I don't know what that is. Okay, we're recording. Okay, so related rates really follow up on implicit differentiation. So we're going to start out with kind of the same problem twice, but with a little twist on it in example 1. So nothing complicated, no fancy rules here. We've got a curve, x squared minus 2y plus 5x equals y cubed minus 6. We want to find dy dx. We know how to do that, right? Nothing to throw us off here. I take the derivative with respect to x. I do not need a chain rule there because I'm taking with respect to x. Then I take the derivative of 2y, and I do need to use the chain rule there because we're taking with respect to x. And then to finish it off, we end up with plus 5 equals 3y squared dy dx. And the derivative of 6 is 0, so we don't write anything there. So whether we do it in 3 or 4 steps to make sure we're right, whether we're good at keeping track of things in our head, I am going to bring all of my dy dx's to the right because then they'll both be positive. And that's going to give me 3y squared plus 2 times dy dx. And then I can leave everything else on the left, and that's just 2x plus 5, and life is good because everything is positive, or normal, a synonym for positive. Don't put synonyms in your coffee is a bad joke. Yeah, Jaden. Synonyms. Cinnamon only. So dy dx anyway is 2x plus 5 over 3y squared plus 2. That is math we've done in the past. Why did the x's get left alone? Or I should say, why did the x's not have to have a chain rule, but the y's did? Because traditionally or conventionally, or because it's just we had to pick one, we take with respect to x, right? That whole math could have been done with respect to y, and the rules would be reversed. We would get good answers, but we would end up with dx dy, which is a thing. It's just not the common thing that we do. Example 1 says to take that same curve and take its derivative with respect to t, a variable that is not anywhere in there. We can do this too. Since there are no t's in there, that means we're going to not leave any variables alone. So doing the same thing, I can differentiate this curve, and I could get 2x, but since I'm taking with respect to t, I've got to write dx dt. So that's really what it comes down to. It's whatever you're taking with respect to, that's the only person who gets to ride when it comes to the chain rule. If I'm taking with respect to a variable that's not there, everybody needs a chain rule. And that's what's going to happen when we do related rates problems. So if you know you're doing a related rates problem, everything is going to get a chain rule. We can clean things up. We don't necessarily need to clean things up. We're not necessarily setting things equal here. I don't know why I gave any more space. We're not looking to have something equals a bunch of other stuff. We could do that. There's nothing stopping us, but a lot of times we don't really need to do that. So that is the answer to the question on example 1. You can do this. In this case, we are thinking about how our x and our y coordinates are changing with respect to time. So we'll do an example of an actual problem. That's kind of how we're going to work today. We'll do just kind of some of the math behind the scenes. We'll do one word problem, but the real word probleminess of this will not come until day 2. Okay. This one I will try to give at least a little bit more context onto what's really going on, why we even care about doing this. So a little bit of a simpler example. Given x squared minus y cubed equals 1, find dy dt in terms of x and y if dx dt equals 4. So this one's given us a little bit more direction. Our goal is to find dy dt, so we will solve for dy dt when we're done. So same deal. 2x, we're taking with respect to t, so we've got to chain rule that with dx dt. Minus 3y squared dy dt equals 0. Okay. So this does want us to solve for dy dt. So I'm going to bring that 3y squared over to the other side, but also switch sides in the process. So this is 3y d squared dt on the left, which I underlined for no good reason. And that would equal 2x dx dt, which I underlined for no good reason. There we go. So bring 3y squared over to the right, but write it on the left. And that is a legit statement. Agreed? So dy dt equals 2x over 3y squared dx dt. Oh, and we did say that dx dt equals 4. So to answer their question, we're going to replace that dx dt with 4. So the final answer to their question should be 8x over 3y squared. That's one of the things to remember in related rates. These dx dt's and dy dt's, they're variables. They're things that you either solve for or you replace with a number. And that is an 8x, despite the fact that it sort of looks like a y. Cool. So then the question that we're answering, and again, we don't have a lot of context here. We are just doing what they're asking us. What is dy dt at the point 3, 2? So dy dt evaluated at xy equals 3, 2. Sure sounds like 8 times 3 over 3 times 4. Which I could multiply and simplify, or multiply and divide out, but I'm going to get rid of those 3's. Yeah, it's just 2. 8 divided by 4 is 2. All right. Okay, so we solved the calculus problem using symbols and math and things we've done in the past. Zero context on what that is. What's going on behind the scenes, or why we would want to do this? Let's take a look at this function in Desmos, that would be Spotify, not Desmos. We've got 3, what was it? 3x squared?
X squared minus y.
Yep. Cool. Y cubed equals 1. It was, yeah, that came out of the derivative or something, right? Yeah, x squared minus y cubed equals 1. There is our function. We are at the point 2, 3. 2, 3, am I right? Nope, 3, 2. I knew when I graphed it, I would know whether I was right or not. Okay. Cool. All right. Okay. So this is a good, if you have a little bit of physics behind you, if you've thought about things moving in physics, this is kind of what's going on here. If you had a particle moving along this path, right, or an object or something was moving along this path, we were given that dx dt equals 4, right? So what we knew, the information we knew was that our particle is right there where the blue particle was. And if you were standing directly under that particle and you were trying to run and stay under the particle, does that make sense? You would be traveling 4 units per second. So that dx dt is the rate that that particle is traveling, but specifically in the x direction. So it's not, if I measured its actual velocity or its speed, I would probably get something different. But I'm not measuring how fast it's actually moving in space. I'm thinking about tracking it from the x-axis, like I'm trying to stay directly under it. Of course, that's an instantaneous speed. I'm not saying that it's happening, you're always traveling 4 meters per second. At the instant this is happening, that's how fast you're traveling, to keep track of it. The fact that we're finding out that dy dt equals 2, we're doing the same thing. We're figuring out the same thing, but for the y-axis. So if I want to keep track of how fast this particle is moving on the y-axis, so if I wanted to, I think the running analogy is kind of lost here. But if I'm at 2 on the y-axis and I want to stay at the same level of the particle, then I would only have to move 2 units per second. That would be the speed you would track on the y-axis. So that gives you a little bit of an idea of what we're doing. These things actually have a reason. We didn't just one day say, hey, let's differentiate with a third variable. We're actually looking at kind of the time rates of that x of t and that y of t. So we're tracking the position, but we're kind of thinking of the components, the horizontal component and the vertical component. And if Bittman or Ziegler have ever said the word vector, component should be a word that goes right along with those. So, this is the math part about it. You got to have some connection to it, but in the end, it's really just, that we're getting the math. So you can see how to do the math. We looked at that in the example, and hopefully that just gives you a little bit of an insight of why would we be bothering to differentiate with a third variable. And the reason we're using t is because we're measuring the rate by time, 4 units per second or 4 units per whatever. There were no actual units in there. Okay. So there's one example. We'll do one more example, and then you'll have some time to work. All right. So the topic is called related rates. The purpose of an equation, and we're going to see, because we're actually going to start using, and day 2 hits this a lot more. We're going to start using like well-known formulas, like the area of a circle. The area of a circle formula tells the relationship between the radius of your circle and your area of your circle. If you're in a relationship, you're related. So that's where this related rates idea comes from. So the area of a circle relates the radius of the circle to the area. Now that we know a whole bunch of calculus, what we can basically do is take the derivatives of these formulas, which is going to give us rates, and those are going to be in an equation, so we're finding a relationship between the rates. So the rate of change of the area, the rate of change of the radius, that's what these problems are. I believe that's everything that I have written up there. So example 3 says, we have a circle and it is expanding and contracting. So this isn't just a circle on the paper. This is a circle that is moving, that is getting bigger, that is getting smaller. So we want to know about those rates. How many inches, centimeters, whatever, is that radius increasing each second? How many square centimeters is that area increasing or decreasing each second? So the way that we do that is we do what letter A says, find an expression for the rate that the area is changing with respect to time. That's just a related rates problem without x's and y's. So we're going to take A equals pi r squared, and we're going to differentiate it with respect to t. So obviously, just a lone variable, if you have A equals, then when you differentiate, you're going to end up with dA dt equals. That's no different when we changed y equals to dy dx, right? Just different variable names. Okay. Sometimes things just feel different because you're using formulas, but what is pi? It's 3.14, but what word am I looking for? Constant, yeah, pi is a constant, right? So it's a coefficient as well, right? This is a number times r squared. R is a variable because, my gosh, we said it's a true variable. The radius is changing, so it's a true variable. I am definitely trying to say that it is not the product rule. Good. If you had used the product rule, you should end up at the same spot, but you would have to know that d pi dt is 0 because pi is a constant. But no, this is just a coefficient. Pi is just a coefficient, so we end up with 2 pi r dr dt. So we have found a relationship between the rate of change of the area and the rate of change of the radius. And it does turn out, and I think this is what's kind of weird about related rates, the rate of change of the area depends on 2 things. It depends on the radius at the given time and the rate that that radius is changing. So we actually need two variables to solve for dA dt. So a bigger radius may mean a bigger, smaller rate of change of that area. That's kind of the key to this. So let's see what a problem actually looks like. They're going to have to give you a lot of information in order to solve these. The radius of a circle, letter B, is increasing at a constant rate of 4 centimeters per second. So you have this circle that was this big at the start, and then a second later, it was somehow a centimeter bigger. And then another second later, the radius itself, I'm like drawing the circle with my hands. You know, the radius of that circle at the start was 7 centimeters. Then after a second, it was 11 centimeters. And then after another second, it was 15, because I can add 11 and 4 because I'm a math teacher, 15 centimeters. That's what's going on here. No, we're just going to plug our information into our formula for dA dt, because that feels easier than, yeah, that's all we're going to do. So let's take a look at this. You should, in the end with these problems, have everything plugged in but one value. And if you don't, there's more to do. But today we're looking at the simple ones. So this problem, as simple as it can be, our radius is 7. So there's two questions here. We want to do 7 and 9. And that's sort of just to point out that it actually changes based on what the radius is. Our radius is 7. Where are we going to plug in that 4 centimeters per second? Correct. Radius is 7. dr dt is 4. And that's all we need to figure out what dA dt is. It's 2 pi times r times 4. Which sure sounds like 56 pi to me. And what would the label on that be? It would not be centimeters per second, because it's the rate of change of area, square centimeters per second. I would imagine in the world of, I wouldn't even imagine. In the world of science, we would really want to, if I was a science teacher, we would be keeping track of all of our labels and getting our label from all of that. But in the world of related rates, we should be able to get our label based on what it is that we're looking for. dA dt should be, like, literally, the label should be a label for area divided by a label for time. And if it's not, then you don't have the right answer. If we did keep track of our labels, we would have that, because the label on 7 is centimeters and the label on 4 is centimeters per second. So when you multiply centimeters by centimeters per second, you get centimeters squared per second. I really don't think we need to go into that I know we don't need to go into that detail in calculus, because as long as we've done all of our calculus correct, our labels should follow. If you've done your calculus incorrect, you're going to have the wrong number here. So it doesn't matter if you got the label correct or not. You know what I mean? So I think that's just kind of how I live in the world of labels. What happens when the radius is 9 centimeters? Same thing, but we're going to get a different result. dA dt this time is going to be 2 pi times 9 times 4, which is going to be 72 pi centimeters squared per second. Adding to the radius adds more area the further out you are. That's what's going on there, right? I mean, that circle is getting bigger and bigger and bigger area-wise. Adding 1 centimeter when the radius is small isn't going to do much, but adding 1 centimeter when the radius is big is going to add a whole lot more, because you have to add that extra centimeter the whole way around the big circle. So it's very common. This rate they said was constant. dA dt is not constant because it changes based on where your radius. Yep, which is why we have to do the calculus. Cool. All right, last part of the example, because everything next is for day 2. The area of the circle is decreasing at a rate of 10 square centimeter, oh, I do have square centimeters written. I was looking for the 2. At 10 square centimeters per second, at what rate is the radius of the circle changing when the area is 9 pi square centimeters? Probably should have written constant there, but in the end, they're kind of implying that. By not saying at time t equals whatever, they're implying that that's constant. At what rate is the radius of the circle changing when the area is 9 pi square centimeters? So let's label what those things are. What are we going to label? What equals 10? Yep, dA dt. And it should be negative 10, correct, because it's decreasing. And then what are we labeling 9 pi? Or what are we setting equal to 9 pi? We already said the dA dt was negative 10. So that's what that's saying, that the radius is changing at a rate of 9 pi? What are they telling us is 9 pi? The area, yeah, A equals 9 pi. Yeah. So a little bit of not a roadblock, but just this is something that can happen too. I tried to kind of pick an easy example to start out with to show all of the things that we'll go into more depth in the later ones. If we try to do the same thing that we did in our previous problem, dA dt equals 2 pi times r, sorry, I know it off the top of my head, but we're following that formula up at the top there, 2 pi r dr dt. Do I have a number to plug in there? Nope. Oh, and actually I should be, right, so I should have dr dt here, and I should have plugged negative 10 in for dA dt, right? I was thinking of the other issue. We don't have r. How do we get r? Nope. Yeah, use the area formula. So this kind of goes back to like in implicit differentiation, when if I knew x but I didn't know y, I had to go back to the original curve. If you don't have the right variable, go back to the original function. If I know that the area is 9 pi, then there's only one possible radius that I could have. What is that radius? 3, right? So I'm going to write it out so you guys have it in your notes, but this is one you should be able to eyeball. If a equals 9 pi, that means that 9 pi equals pi r squared. Well, divide both sides by pi, and then take the square root. R equals, radius can't be negative, so r equals 3. That kind of goes back to what I started with here. You know, a formula is a relationship between the two variables. If I know one, I should be able to get the other. That's if there's only two variables in the formula. But that's kind of the key. So sometimes you'll have something spelled out and you'll be missing a variable, but you have the information to get that variable from the original equation. So it sure sounds like dr dt equals negative 10 over 6 pi, which I could rewrite as negative 5 over 6 pi. Yep. Probably, if I cared about doing math correctly, I would have put a 3 there. But it's Friday, so yeah. You know, it's definitely not a friendly number, but that is the rate at which it's changing. Those signs are important because, again, this is a really, really simple example. Obviously, if the radius is getting bigger, the area has to get bigger. If the radius is getting smaller, the area has to get smaller. But not all relationships work like that. There are some where one thing gets bigger. We'll see this definitely when we do the ladder problem on Monday. One thing gets bigger, but that causes the other thing to get smaller. So that's when your signs can be really important there. And obviously, I shouldn't say if you're in an FRQ, because honestly, there's a specific style of FRQ questions where they really try not to dwell on past knowledge. So, but I guess, anyway, I'm rambling. I'm thinking out loud. Signs are important. I said so, and that's why they are. And we're going to end it as that, right? I'm the person who gets to say those things. So, okay. I love rambling. Okay, that's it. So I do kind of have the